Okay. I'm planning to put my lecture notes online at a certain point when I organize them. The thing that prevents me is that I have a deadline. So I don't have much time at the moment, but it will be over this week. Now, share screen. Yeah. Share. Okay, good. Can you see my screen? Can you see my screen? So where were we? We're talking about decays and scatterings. Which are amongst the fundamental phenomena that is being studied in particle physics. Let me just move that a little bit so I clear myself slightly more space around here. Okay. We spoke about lifetime of a decaying particle. Right? We said that tau is 1 over gamma, where n is n0e minus gamma t. We spoke about the uncertainty in the mass of a decaying particle. Right? We said that the wave function is described by the Bright-Wigner function. This is something which is internal to the particle, right? It's not something because of the measure. Psi of m squared is 1 over m minus m0 squared plus gamma over 2 squared. This is the Lorentzian or Bright-Wigner. We started to speak a little bit about scattering. Right, I introduced the concept of, well, we discussed a little bit about the, the classical Rutherford scattering experiment. Right, Rutherford. And we introduced experiment. Let's write it. We introduced the concept of a cross-section, which is a measurable quantity. And has dimensions of area. And of course, most importantly, we can calculate it theoretically. So this is a way of connecting the theory and the experiments. Right. Then we discussed a few experimental issues, such as a thin target versus thick target. And we defined the beam flux. Phi as the number of particles sent to the target per unit time, per unit area. Number per unit time, per unit area. And the luminosity, which is the flux multiplied by the number of target particles. By number of target particles. L is phi times n target. And then the rate of scattering events that we have, dn scattering over dt, is just the cross section times L. And then I gave you one classical example, right? That of a point-like light particles which are in a beam that hit a target particles that are heavy and spherical with radius r. So example one we had was light particles that go and hit a target of some radius r, right, which is spherical. And the scattering is defined if the particle actually hits the target, the billiard ball hit, in which case then intuitively we get that the cross section is sigma is just pi r squared. Another classical example is the measurement of scattering into a solid angle. So example two, I just give it to sort of complete the recap. Right, so I have two particles, right? So one is moving right in the beam and it's being scattered into some solid angle, right? So you set at the solid angle here, right? This is theta, and this is of course d omega. All right. So if this is theta, well, this is d theta. Why did erase it? All right, this is d theta. All right, we have d omega. It's just sine theta, d theta, d phi. Right, so we need to do like here we have sort of again a beam. So we do something like that. Of course, this is the impact parameter. This is a different color. This is the impact parameter B, and that would be dB, right? And that area would be d phi. Right? And that cross-sectional area, this is d sigma. So, classically, right, the scattering angle is fully determined by the impact parameter. We can carry the calculation according to Newtonian laws. Right? Now the cross section is the size of the aerial element which the particle must collide in order to be scattered at angle theta to theta plus theta. So this is theta, and this would be theta plus d theta. So we said that classically, right, the cross section is the size of the area or area element in which the particle must collide. In order to scatter at angle theta to theta plus d theta, right? So from here, from the cartoon, right, d sigma scattering is just b, which can be a function of theta times db times d phi. Right. This is the sigma. But this is the area, the sigma. Now, since the omega is sine theta d theta d phi, right, I can basically divide them and write down the sigma d omega. I'm not really dividing; it's just a quickest way of showing it, although it's a bit rough. It's b of theta over sine theta, and then dB over d theta. Just to give you a feeling. Right, so we just need to use some classical physics to find out what is b of theta, right? So once b of theta is known, we can put it into the equation and find out the sigma d omega, which is of course called the differential cross section. Right. There's no real differential here when you think of it. It's just describing the angular dependence of the cross section in the scattering, which plotted here is elastic scattering. Just the angular dependence of the cross section. In an elastic scattering. Now, the really important thing to remember is that, you know, classically at least, everything is determined once we know the impact parameter B, but practically we don't really have a way of measuring the impact parameter. What we can measure is this is the cross section. But of course, at least classically, they are dependent, right? Once you know the cross section, what is the impact parameter, and vice versa. So, you know, this is not just for elastic scattering, of course, right? We can ask various questions, right? So, for example, if we have an inelastic scattering, it is limited to elastic scattering. Of course, right? I mean, for example, if we look at the creation of a Z boson via inelastic scattering, you know, for example, proton-proton collide and produce a Z plus something else, right? Proton plus proton produces Z plus whatever, X, right? We can ask what is the total cross section, or what is the total, or what is the cross section as a function of the momentum of Z? Ask, right, e.g., right, what is the sigma over dp z, right? The cross section as a function of momentum, etc. Right? Or, you know, if we have UV photons that heat us, heat the skin, right? We can ask what is the cross section for some dangerous mutation to happen. Right? If we know the answer to that, then we know what is the flux of photons that arrive to our skin from the sun, then we can calculate what's the probability of getting cancer or something bad, that thing per year, of course. All right, this was a quick recap with things that I needed to complete from last time. Any questions? No? Okay, it's quite easy, so it's not very technical, so I don't expect many questions, but just to make sure that you're all with me. Okay, so what I want to do today, I want to do the quantum mechanical treatment, and that goes to Fermi's golden rule. No, I think I told you I had a little bit of thought with myself whether I should fully derive Fermi golden rule, because it's normally being derived in quantum mechanics course, or I just speak about it, which is what typically being done in this course. So right now, what I'm going to do is I'm going to speak about it, and if we have time, I'll put a tutorial or an appendix or sometime when I'll derive it. But that depending on how much time we have. The reason why I'm deriving it straight away is because it's something which, as I mentioned, is derived in standard quantum mechanics course. So you're supposed to learn it, or will learn it, in the second semester, if not now. And because I want to focus really on the things of interest to us. So I'll actually explain it to you more than derive it right now, but if I have time, I'll derive it later on. So, we know that particles are quantum objects, right? And we want to know what's the probability for a quantum process to happen, right? So, something like a radioactive decay or scattering of two elementary particles. So the calculation, as stated, is called the Fermi's golden rule, and it really depends on two ingredients. So let me write it down. The probability of a radioactive decay event or scattering event is called, was first derived by Fermi, of course it's Enrico Fermi, right? Fermi, and is called Fermi's golden rule. I know what is the other reason why I'm not going to derive it right now, because you can derive it in the framework of classical quantum mechanics and in the framework of quantum field theory, and it's a bit different. So normally what you learn is to derive it in the framework of classical quantum mechanics. I will actually give you all the rules how to derive it in quantum field theory, but this I definitely would not be able to discuss in this course because that requires some deeper knowledge of quantum field theory. So it's one of those cases where I give you the outcome. So you know how to do it, but in order to get the full derivation of it, you have to learn quantum field theory first. So the Fermi's golden rule depends on two ingredients, right? It depends on two ingredients, right? So the first is the amplitude. One is the amplitude, denoted by M. It's also called the invariant amplitude or the matrix element. Matrix element. That's also, you see that in textbooks a lot. TFI. It's transition matrix element. By the way, how many of you have studied Fermi's golden rule? I think I asked you, but I don't remember the answer. Who studied it? Raise your hands. 1, 2. 1, 2. That's all. So nobody. There is one with no camera, so I don't know if you raise your hand or not. 2 studied, and the rest did not study it. Okay. Is there any question? I see the one is still raising your hand. No. Okay. So I may put it in one of the tutorials, but I'll have to see. So the amplitude M. The amplitude contains all the dynamical information, right? It contains all the dynamical information, right? I'll show you how to calculate it using the relevant Feynman rules, which are derived from the relevant Feynman diagrams, right? It's calculated using Feynman rules, which are derived from the appropriate Feynman diagrams. The second part is the available phase space for the process. That's also known as the density of states. Basically, it tells you all the kinematics information. If a particle decays, then to what particles it can decay. Essentially, it tells you the probability of decaying into each of the possible final outcome is identical. That's why the sign is called the available phase space. Available phase space. Right. This is known as the density of final states. Right. That contains all the kinematics. The mass, energy, momenta, masses, energies, momenta, of the particles, of the outgoing particles. Well, of all the particles, incoming as well. It reflects the fact that a given process is more likely to occur if there are more available options, basically, for the particles, the final state. So a given process is more likely to occur if there are more available options. Or available channels, really, I should say. So, for example, if we're talking about the decay of a heavy particle into lighter ones, there is a large phase space, basically. But if we speak about the decay of the neutron, right, the neutron decays into a proton, an electron, and antineutrino, there is no extra mass to spare in some basic sense, right? So the available phase space is actually very small. So in essence, right, the Fermi's golden rule really states that the transition rate from the initial to the final states is given by the product of the phase space and the absolute square of the amplitude. So let's use it, and then I'll introduce it and show you how to use it. And as I told you, if we have some time, I'll actually do the derivation, this from the quantum mechanical derivation. Questions? No? Okay. So let's write down the golden rule for decays. So we have a particle. We can assume it's at rest. It's just a choice of reference frame, right? Which decays into several other particles, right? So we have particle 1 that decays into 2, 3, 4, n, right? Decays into n minus 1 particles. Then the decay rate again, it's measured in the particle's rest frame, is given by gamma is capital S over 2 m1. Then we have integral over m squared, and then 2 pi to the 4 delta for P1 minus P2 minus Pn times multiplication, so pi from j equal to 2 to n of 2 pi times delta Pj squared minus Mj squared times theta of Ej times d for Pj divided by 2 pi to the 4. That is the golden rule. Now, let's go one term by one term and see what it means. Let's put it in the gold or yellow. Okay, so Mj, that's obvious. That's the mass of the J particle. Pj, of course, is the 4 momentum, the J particle. Of course, Ej is just Pj, the zeroth component, is the energy. Right? Now, S, the capital S is a statistical factor that corrects for double counting. So when we have identical particles in the final states, right? So S, this is a statistical factor that corrects for double counting. When there are identical particles. In the final state. So if we have S, small s identical particle, for small s identical particles, S is 1 over S factorial. Now, if we don't have any identical particles, then what would be capital S? 1. No identical particles. No identical particles means that S equal to 1. M is the amplitude. Which is really a function of the various momenta. Right. As we said, this contains all the information about the dynamics. Okay. Now, everything else I believe that you know here, right? The delta function is a delta function. A theta function gives you 0 and 1, right? So theta of Ej, right, is 1 if Ej is greater than 0 and 0 if Ej is smaller or equal to 0. And the delta functions is just delta function. Okay, and the choice, of course, is the rest frame, which is the natural choice when we speak of a particle that decays. because it doesn't have any interaction with anything else. It just decides to decay. Now, except for this m for the amplitude, right? Everything else is a phase space. If you look for a moment at what we have here, it's just a phase space, right? It just tells us that we have to integrate over for all four momenta, right? This is the pi, right? We're multiplying over all to have integration, continuous integration over all four momenta. So there are many integrals here, really. But these are subject to three kinematic constraints. So really, the golden rule is about phase space, right? So except from M, right? Everything else is a phase space. Right? You basically integrate over all outgoing four momenta subject to three kinematic constraints. Right. So the first constraint, you can see it from here. Let me write it down. This is the first constraint. And this is the second constraint. And this is the third constraint. So what are these constraints physically mean? Let's see. So constraint number one, right? Here, right? This just states that each outgoing particle, right? I'm multiplying over all the outgoing particles. These are real particles. These are not virtual particles, right? So it must lie on the mass shell. So pj squared, which is e squared minus pj vector squared, right, is just the mass squared, right? So one is that each outgoing particle is real. So pj squared just ej squared minus pj squared is just mj squared. So this is the meaning of this delta function, right? So delta pj squared minus mj squared is just delta of ej squared minus pj vector squared minus mj squared. The second constraint here, what does it physically mean? What is the physical meaning of this constraint? Any idea? Well, it certainly means something.
That particles have energy, positive energy?
Exactly. That each of the outgoing particles energy is positive. Very good. each of the outgoing particles. Energy is positive, right? Pj 0, right, is Ej must be greater than 0, right? Remember that the theta function of Ej will give us 1 if Ej is greater than 0, and 0 if Ej is not. Okay? We cannot have particles with negative energies in the decay process. And the third constraint, reminding you, that's a simple constraint.
Momentum conservation.
Exactly. This is, well, it's a 4 momentum, so it's really energy and momentum conservation. So the third constraint, right, this is energy and momentum conservation, right? So the delta, right, delta 4 P1 minus P2 minus Pn, right, and just find mu from 0 to 3, delta function of P1 mu minus P2 mu minus Pn mu, right, which is just delta E1 is equal to minus E2 minus Vn times by I from 1 to 3, delta of P1I minus P2I minus Pni. Right, so this simply states that the energy of the outgoing particle is equal to the energy of the incoming particle, and the momentum, the sum of momentum of the outgoing particle is equal to the momentum of the initial particle, right? So really, when you think of it in these terms, I think it makes much more sense now that you look at the golden rule. Well, it just says that all the outcomes that are consistent with these 3 constraints are essentially equally likely to occur. That's what the golden rule states. It's very simple in the end. So the golden rule states that all outcomes consistent with these 3 kinematic constraints are equally likely. It's that simple. Just one more comment, I see, for the 2 pi's. So again, you learn that this is really a convention. So I'm using, again, a standard convention in textbooks. There are other conventions, actually, so it depends which textbook you're looking at. So for the 2 pi rules, so every delta function gets a 2 pi, and every integration, d, gets a 1 over 2 pi. As you're going to see, these are actually going to cancel each other. So these are the convention that we're using. Convention. You want the 2 pi convention. Right? Every delta function gets a 2 pi factor, and every integration gets so integration, that means d, right? D something gets 1 over 2 pi. So this is the convention that they will cancel each other. Now we can take the golden rule and slightly simplify it. Okay, so this is just the convention that we have. So let's take the golden rule.
So is the convention for one-dimensional or for four-dimensional deltas and
four-
integrals?
Delta is four-dimensional. We have 2 pi to the 4 because delta is delta to the 4.
Okay.
Each dimension gets a 2 pi. Okay. Now, okay. Now let's take that and simplify that a little bit. So the way to simplify, let's see, I have a way. No, there was a way here, which I can do that. What happens? Nothing much. If I do that, what happens? Oh, great. I can do a copy. Now I can take it and paste it. Woohoo! It's a great technology. Okay, so now let's make some simplification. So simplification.
Asaf?
Yeah.
One question.
Yeah.
You said that all the decays are equally likely. But in the PDG that you gave us to look at in the homework, it talks about decays that are very common and some that are almost non-existent. So how does that work?
No, what I mean is that all decay channels are equally likely. Now you have particles that, we discussed that in the last time, or one before last time, and in the tutorial. Of course, in order for a decay to exist, right, it has to obey all the rules, all the conservation rules that we discussed, right? If you have a particle that that does not obey the conservation rules, right, the lepton number, lepton family number, etc., then obviously this is not going to happen. Only the rules that only the decay channel that can occur are only those that obey all these conservation rules that we have. But if you have multiple, if a particle can decay via several channels, for example, the tau particle can decay into a muon or into an electron, right? Plus the corresponding neutrinos, right? Now, you have a much larger phase space. What the Fermi tells you basically is that you have to look at the entire phase space, right? And each of the possibilities that appear in the phase space is equally likely, right? So since the electron is lighter, then you have more phase space options, right, to split the energy between the tau and the neutrinos. Then between the electron and the neutrinos, then you have between the muon and the neutrinos. Right, so this is what the Fermi golden rule tells us, basically, that when we look at all these decays that are legal, so they are not violating any of the conservation laws, then you look at all the possible channels, they are equally likely. And when I say channels, I mean, how the momentum is split among the decay products. Okay, so think of it, maybe I simply have to derive the Fermi golden rule, or you have to simply read about it. You just look at, it's just a phase space. If you have a possibility of decaying into, I gave you the example of the neutron decay as an example of a decay that doesn't have many channels because the proton mass is very similar to the neutron mass, right? So you cannot have a situation where the proton has a little energy and the electron has a lot of energy, right? But if, let's say, the proton was much lighter, then you could divide the energy in different ways among the proton and the electron and the neutrino, so you have more options to split it, and then it will be more likely. That's what it means.
So if I understand, you have, let's say you have 100 different channels, and you could have that 70 go to give you one specific product and 30 give you another. But each single phase is equal in likeliness.
Correct. Yes, you understand it properly.
Thank you.
What about the matrix element?
Well, okay, that depends on the matrix element. Well, the matrix element, we said that will take care of all the dynamical, right? This will eventually tell you if you can or cannot do that, right? That if you're violating anything, it will be 0. If you're not violating, then it will not be 0. That's exactly that. I'm going to calculate that. I don't know if today or the next lecture. Well, I'm going to show you how to calculate the matrix element from the Feynman diagram. That's where the coupling constant enters that we have in each vertex. Right? These T's we describe, or the alphas, they are going to get into the calculation of M. All right. So let's do more questions. Oh, okay. So let's do a little bit of a simplification, slight simplification of this formula. So we have integral over d4p. So d4p, I can write this dp0 d cube p vector, which is just dE d cube p, or dp vector. Now, since we write explicitly dE is dp0, and we can carry explicitly the integral over dE. We can carry explicitly the integration over dE, and we do that using the delta function. So when we have a delta of p squared minus m squared, right, this is just a delta of p0 squared minus p vector squared minus m squared. So we can use the delta function, but we have to be a little bit careful because we have the integral over dp0, and the delta is over p0 squared. So we use the identity which you can find in any mathematical textbook. The delta of x squared minus a squared is equal to 1 over 2a times delta of x minus a plus delta of x plus a, provided that a is greater than 0. So again, this is a mathematical identity of a delta function. Open your favorite mathematical handbook text and you'll find it there. And then we have this multiplication of delta times theta. So we have theta of ej. So ej is just p0. I'm omitting for the calculation the j index, right? Times delta of p0 squared minus p vector squared minus m squared. This is equal to 1 over 2 square root of p vector squared plus m squared. Right, that's 1 over 2a times delta of p0 minus square root of p vector squared minus plus m squared. Now, what happens to the second term in the delta?
The theta takes care of it.
The theta killed it, right? Because it has a negative energy, right? Here, p0 is equal to p squared plus m squared. And the other term is p0 equal minus p squared plus m squared. So this is negative, so that the theta function killed it. Okay. So this delta function, now we can cancel with the integral over dp0. Right, so we have now a delta function of p0 and we cancel with the integral of dp0. And we end up It's writing that gamma, right, is S over 2n1 integral m squared times 2 pi to the 4 times delta to the 4 p1 minus p2 minus pn. We haven't touched that, times pi j from 2 to n of 1 over 2 times square root of p squared plus m squared. And well, now I have to keep back in j, right? So pj squared plus m squared j. And then we have just in 3 integral d cube pj over 2 pi cube, right? One of the 2 pi was cancelled. And now we still have one delta function, right, which we can use every time we're seeing pj0 or ej. Now we don't see pj0 here, but you can have a pj0 inside M, right? So every time pj0 j appears inside M, we use the remaining delta function. And to write, pj0 pj squared plus mj squared. Now, in fact, this equation here is more useful than the original golden rule for practical purposes, but I did not state it. I just stated the golden rule because the golden rule makes the physical intuition of what's happening there is much easier pronounced than if I write down this equation. All right, questions? Okay, let's do an example. It makes things easy to understand. So example. So 2-particle decay. It really means that there is a single particle that decays into 2 particles, right? That simply means that n is equal to 3. Right? So particle 1 decays into particles 2 plus particle 3, which is the simplest that we can think of. So let's put this in the equation 18, in the equation here. So it's star, use star. So gamma is S. Now the factors of 2. So j is equal to from 2 to 3. So we have it twice. So we have here another 4. We have 2, 3 instead with 2 to the power 6, but here we have 2 to the power 4. So they cancel out. So we have another 4, that's 16, 2 is 32. So I have 32 and then pi's, right? So pi to the 4, and here we have pi to the 6. So we end up with pi squared m1, and then we have integral of m squared delta 4 of p1 minus p2 minus p3 divided by, so it's a multiplication, so it's square root of p2 squared plus m2 squared times square root of p3 squared plus m3 squared d cubed p2 d cubed p3. Okay. You all with me? That's the integral that we need to solve. We have a 4-dimensional delta function, but here we only have an integration over 3-dimensional real space, right, through real momentum. So what we do is we simply write down delta 4 of P1 minus P2 minus P3. It's just delta P1 0 minus P2 0 minus P3 0 times delta cube P1 minus P2 minus P3, right? Now, we argue that we work in the rest frame of particle 1, which of course considerably simplify things in the rest frame of particle 1. Then, of course, we have what is a P1 vector?
0.
Of course, right? P1 vector is equal to 0, right? And P1, the 0th component, what is it?
Mass.
Right? It's just E1, which is just the mass of particle 1. So automatically, at least from the last delta function, then we have delta cube of P1 minus P2 minus P3 is just delta cube of P2 and plus P3, right? Which obviously states immediately that P2 or P3 is equal to minus P2, right? And so we can automatically cancel the integration, use the delta function to cancel the integration over dp3. So cancel the integration over dp3, right? Now, since we have E1 is equal to M1, so 1 and 2. So 1, we have that. 2, we have E1 is equal to M1. Then we end up the delta of P1 0 minus P2 0 minus P3 0, right? Is just equal to delta of M1 minus, well, P2 0 is just P2 vector squared plus M2 squared minus square root of P3 vector squared minus plus M3 squared. All right, is that clear to everybody? What I'm doing here? So we plug that back in the calculation of the decay rate, and we end up with a gamma. We had S, so gamma is S over 32 pi squared M1, and then integral M squared, and then we have this delta M1 minus square root of P2 squared plus M2 squared, and sorry, minus square root of P3 squared plus M3 squared, right? Divided by square root of P2 squared plus M2 squared times square root of P3 squared plus m3 squared. Right, we have it from here. And then we still have the remaining delta cube of P2 plus P3 times d cube P2, d cube P3. So we use now the delta function to integrate over dp3, right? Use the delta function to integrate over dp3. Well, dq p3, of course. Then we end up with gamma, which is s over 32 pi squared m1, integral of m squared delta m1 minus square root of p2 squared plus m2 squared minus square root of p2 squared plus m3 squared, right? Because of the delta function, I could replace p2 and p3, it's a squared, so it doesn't matter, right? And the same in the denominator. Square root of p2 squared plus m2 squared times square root of p2 squared plus m3 squared. And now we're simply left with integration over d cube p2. That's the nice thing about these things. You start with a very nasty integrals, but then you have made plenty of delta functions, and you end up not having to do, well, as you're going to see, we're not going to make any integration at all. So we still have to do the integration over d cube p2. So in order to proceed, again, it's best to work in spherical coordinates, but it's really spherical coordinates in phase space, right? Because it's p is the momentum. So to proceed, we use spherical coordinates. Right, remember, it's a phase space really. So P2 vector, I will write it using P, theta, and phi. And that is allowed, and it's always allowed, of course. It's useful because everything we have here depends on P2 vector squared, right? On the magnitude of the vector. So everything makes sense. Makes sense. Since all terms depend on P2 square, which is just P squared, right? Specifically, this is true because the matrix element M is a scalar. The only scalar you can make from a vector is the dot product of the vector with itself, right? So M, since M is a scalar, then M is M of P2 dot P2, which is just P squared. So we can do that. So M is M of P. So if we do that, then integral, or yeah, d cube P2, right? It's integral P squared dP and times integral sine theta d theta d phi. Right? You should really write P theta and P phi, but hopefully you understand what I'm doing. Now the angular integrals are pretty straightforward, right? So an integral from 0 to pi of sine theta d theta. How much is that?
Two.
2. Thank you. Integral from 0 to 2 pi of d phi is just 2 pi. So surprise, surprise, we end up with the 4 pi term, which cancels with the 32 pi squared. So we have gamma is just s over 8 pi m1 integral of m of p squared, and then the delta, right? m1 minus square root p squared plus m2 squared minus square root p squared minus m3 squared divided by square root of p squared plus m2 squared times square root p squared plus m3 squared, and then times p squared dp. Okay, we're nearly there. We still have one delta function, which we did not use, which is great because we're going to use it to cancel the last integral. But in order to do it properly, we use a trick. So use a trick. So we write down, we make a change of variable, essentially. So we change variable to u, which is defined as p squared plus m2 squared plus p squared plus m3 squared. And then du, right, is just u times p divided by square root of p squared plus m2 squared times square root of p squared plus m3 squared times p. Which you can check by immediate substitution. And again, using these results in gamma, then we end up that gamma is s over 8 pi m1 times integral. Okay, I need to set the boundary of integration. So p is equal to 0. That means that u is equal to m1 plus m2. So it's m2 plus m3, m2 plus m3 to infinity. And that is because p equal to 0, that is u is equal to m2 plus m3. So these are the boundaries, right? So we have m of p squared, we haven't touched that. And then we have delta of m1 minus u times p over u du. Which looks much nicer than previously. Right? Of course, the delta function now simply gives u is equal to m1. So delta function implies that u is equal to m1. And we can use that back in the definition of u here. And if we do that, then we find out that p, which we write as p0, just 1 over 2m1 square root of m1 to the 4 plus m2 to the 4 plus m3 to the 4 minus 2 m1 squared m2 squared minus 2 m1 squared m3 squared minus 2 m2 squared m3 squared. Right. This is simply plugging that in the equation here for you. So this is, again, small homework for you to check it out. I checked it out, but don't believe me. Just plug it in and see that that's what you get. So, you know, P here, right? Remember, P here is a particular value of P2, right? Which is consistent with the conservation of energy, right? P, right? P0 is a particular value of the magnitude of P2, which is consistent with conservation of energy. And so we can simply plug it into the delta function, right? And the delta function really kills the integration over over u, right? We have only one u in the denominator, which is now turned into an m1. So finally, right, we get that gamma is s over 8 pi m1 squared. Right, now we have the magnitude of P times the matrix element squared. That's it. Well, I think this is beautiful because I ended up not doing any integral when you think of it, except from the angular integration for the phi and the theta, right? But we didn't have to carry any integral. I mean, it looks quite annoying. Think how many integrals we had at the beginning. But, you know, we had enough delta functions, which essentially cancel out everything. So we didn't have to integrate at all. Again, kind of makes sense because in this case, what do we have? We have a single particle, which we're looking at the rest frame. So it's just sitting there and then it decays. So it decays into two particles and they have to have the same magnitude of momenta and the opposite direction. And of course, the energy needs to be conserved. So we have enough conservation here that tells us everything, right? Again, the dynamics is in the matrix element. This will tell us the probability of the decay itself. But that we're going to calculate from the Feynman diagram. Not sure if we'll have time today. If not today, we'll do it on Thursday. Okay, just a few more comments. So comments, just final remarks on that comment. So I said M depends only on the magnitude of the vector P2. That is not exactly accurate because it may depend also on another vector, which is the angular momentum of the decaying particles, right? So M may depend not only on P, but also on J, right? The angular momentum. Of the decaying particle. Which I happily ignored in this calculation. So we may construct another scalar, which is P dot J, right? So we're not only obliged to just one scalar. Now this, of course, set a direction, right? Because we can say that P dot J has a preferred direction, which is, you know, call it the Z direction. Of course, if the case, then I can no longer use carry happily the integration over the theta because now it's not a spherical symmetry. So it just complicates my life. or everybody's life. I said we did not solve really any integral. This is 1, 2. We ended up integral. Again, we had the opposite momenta of the outgoing particles. We had conservation of energy, and you know, as long as the decaying particle is a scalar particle, right? It's not a vectorial particle, doesn't carry any angular momentum, then we don't have any dependence on their orientation. So it was easy. Of course, if a particle decays into more than 2 particles, then we do have to carry full integration. We will not be able to escape it. Questions about that? Any questions? I mean, you know, last lecture was more like a storytelling, so I didn't expect that you have many questions. But this now we're getting somewhat into more technicalities.
I have a question.
Yeah, please.
The final result of the decay rate, it depends on the momentum, and this, if I understand correctly, is the momentum of the decay product. So it has no index, but you called that the original P2, right?
Yes. Yes, it's yeah.
But if I understand correctly, if a decay, we're working in the center of mass frame, so there's a particle at rest and then 2 fly apart, but they could have pretty much any momentum as long as energy is concerned, right?
Oh, no. You have this equation. Right? This is really, you can think of it as being dependent. You know, this is a value of the momentum, which depends on the masses of the particles, right?
And this is the only momentum that you can get from this decay?
Yes, this is the only one that is consistent with
conserving both energy and momentum.
Yes. Right. This magnitude here enters the decay rate. So if a particle decays into, note that this depends on the masses of the particle. So you have M1
right.
is the.
So it's a parameter of the problem. It's not something you can tune.
Exactly. So, you know, if a particle decays into other particles, you know, if you have several options to decay, right, then this will get a different value.
Oh, I see. But given that mass M1 decays into masses M2 and plus M3, the final momenta, not just the relative momenta, but the actual momenta of both particles is fixed.
Yes, this is fixed. This is fixed by the kinematics.
Okay. Okay, thanks.
Okay. More? Okay, then we have enough time to go over the golden rule for scattering. As you see, I'm not going to derive it. I'm going to state it, and then we're going to manipulate it a little bit, like we did with the golden rule for the decay. And fortunately, it's going to be very similar. This is not really surprising to anybody. There's a slight difference. So let's speak about, again, golden rule for scattering. Right, so again, suppose now we have 2 particles that collide. So particles 1 plus 2, they collide and produce set of particles 3 plus 4 plus n, right? Of course, what we care about, what we're interested in, is to calculate the scattering cross-section. And that is calculated in a very similar way to the golden rule for the decay. Again, the calculation, in fact, from a quantum field theory point of view is exactly the same. There are a few factors which, again, we didn't derive them, but we have to go through the entire quantum field theory to see exactly where it comes from. So I'm just avoiding that. So the cross section for the process is given by sigma. It's just s. It's the same as we had previously, divided by 4. Now we have square root of p1 dot p2 squared minus m1 m2 squared times integral of m squared, and then again we have times 2 pi to the 4 delta to the 4 p1 plus p2 minus p3 minus p4 minus pn multiplies by integrals multiplying all the over all the outgoing particles j from 3 to n of 2 pi delta pj squared minus mj squared theta pj0, and then d4 pj divided by 2 pi to the 4. So again, pi is the form momentum of particle I, having mass mi. Statistical factor s is the same statistical factor that we had previously. Phase space is the same. So again, we can perform all the pj0 integrals. So let's first say this is the golden rule. Right. Now we can perform all the pj0 integrals. That again the same way as the same method as we did previously. So performing all the pj0 integrals. There's no need for me to repeat those again. You can simply go over the calculation at home or read it in a textbook if you like. Then you end up that sigma is s over 4, again, square root of p1 dot p2 squared minus m1 m2 squared integral m squared times 2 pi to the 4 delta 4 p1 plus p2 minus p3 minus pn multiply by pi j from 3 to n. By the way, you're familiar with this pi thing, right? Multiplication of. Yeah, right? Is there anybody who's not familiar with that symbol? Like a sum, but multiplying, right? J j from 3 to n of 1 over square root of pj squared plus mj squared d cube pj over 2 pi cube. And again, pj0 is just square root of pj vector squared plus m squared, mj squared. Right? Every time we see it, whether it's inside the delta function or inside the m. Okay, so again, we can take the example, and the simple example is a two-body scattering in the center of mass frame. Right? Right. So if we think of the scattering process, 1 plus 2 goes to 3 plus 4. Right? So in the center of mass frame, right, we have that P2 is minus P3. Sorry, minus P1. Please correct me if I make stupid mistakes. Right. So that's square root of P1 dot P2 squared minus M1 M2 squared is just E1 plus E2 times the magnitude of P1. Simple direct substitution would give it. I just did it, just do it. In that case, we have for the cross section sigma, again, very similar to what we had previously. Sigma is S over 64 pi squared P1 plus C2 P1, and then integral of M squared 2 pi to the 4 delta 4 P1 plus P2 minus P3 minus P4 divided by, as we had here, so square root of P3 squared plus M squared, then square root of P4 squared plus M4 squared, and then integral d cubed P3 d cubed P4. So I simply substitute in here. Right, hopefully I did not make any confusion with the 2 pi's, but it's just a substitution. And then we're really repeating the same, exactly the same thing as we did previously, right? So we just write down the delta function, delta to the 4. So delta to the 4 of P1 plus P2 minus P3 minus P4 is just delta of E1 plus E2 minus P3 0 minus P4 0 and times delta cube. Since P1 plus P2 are 0, so we just end up with P3 plus P4. Right? P1 plus P2 are equal to 0 in the center of mass frame. Right? So we can use that to carry the P4 integral. Right? So P4 becomes minus P3, which is obvious. The outgoing particles in the center of mass frame have the opposite momenta. And so we end up with carrying that. We end up with sigma is just S over 8 pi squared. Again, check me with the, I'm not going now carefully over all the pi's, so just check it out that I didn't make anything stupid here. E1 plus E2 P1, and then integral of M squared times delta E1 plus E2 minus square root of P3 squared plus M3 squared minus square root of P3 squared plus M4 squared times 1 over P3 squared plus M3 squared square root of P4 or P3 squared plus M4 squared d cubed P3. Now, M can also depend on the, not just the magnitude, but the orientation or the direction of P3. So we cannot simply carry the angular integration. Let me write it down, since M may depend on the direction of P3. You cannot simply carry the angular integration. But the good thing is that we often don't care about the angular integration because that gives us the full cross-section. What we care about is the cross-section per unit solid angle, right? But what we really want, we mostly want is the sigma over the omega. So we don't really have to carry the angular integration, but simply write. So writing dp3 just p squared dp d omega, then simply avoid the angular integration by writing down the sigma over the omega, just s over 8 pi squared e1 plus e2 p1, and then integral 0 to infinity of m squared delta, and we have the same delta here, right? Of the same delta that we have. Let's write it down. Times integral of m squared delta e1 plus e2 minus square root of p squared plus m3 squared minus square root of p squared plus m4 squared divided by square root of p squared plus m3 squared, and then square root of p squared plus m4 squared times p squared dp. But this is exactly the same integral that we had previously, right? Simply exchange m1 with e1 plus e2 and m2 with m4, and that's what we got. So we already solved this integral. So we got that the sigma over the omega is just 1 over 8 pi squared times s times m squared divided by e1 plus e2 squared times pf over pi. So pf and pi are the magnitudes of, it doesn't matter which one because they're the same, right? The magnitude of the one of the outgoing particle and the magnitude of the one of the incoming particles. Pf magnitude of either outgoing particles momenta, and the same pi either incoming. All right. So in fact, once you do the calculation once, it's the same calculation for both the scattering and the decay. I would say that the main difference is in the scattering, you work in the center of mass frame, and in the decay, well, it's all the difference, right? You work in the rest frame of the particle, which is the center of mass frame. Okay, I think this is a good time to stop because I think I already ran out of time a little bit. Any questions? Any questions by everybody? By anybody? No? Well, then no. Then in that case, I think we can stop here. We'll stop the recording.